What's up, guys? Another day, another banger. It's Mr. Epstein, and I'm back. I'm here with my friend Kevin, and we're going to teach you about solving trig functions. Last week we looked at evaluating them. Now, evaluate is a weird way to say they give you an angle and they want a ratio. Now we're flipping the process. What does solving mean? Solving means, Kevin, get out of here. Means they're going to give you the ratio and you're going to try to figure out your answer will be the angle. So we're kind of doing what we did last week, but just in reverse, which is very common in math. You learn to do a process and then you learn to do it backwards. Okay, so here we have another surprise guest. Who is it? Who can it be? Who can it be? Oh. All right. So, what are we going to start with? All right, I'm going to show you some quick problems. Sine of 60 degrees. Sine of 120 degrees. Sine of 420 degrees. Sine of, hey, are you laughing? Stop laughing. Okay, sine of, what do we got? 480 degrees. And finally, sine of negative 300 degrees. Okay, go ahead. Pause this video and evaluate these trig expressions. Draw a little unit circle and see what you get. Okay, pause it and do it. Okay, did you do it? What did you get as your answer? We can just look at the first one. We could say, sine of 60. I can do it kind of quickly over here on the side. We'll be in quadrant 1. That's nice. So here's our unit circle, 60 degree right there. Draw my right triangle with a vertical segment, 60 degree central angle. Fill in your ratios. We got 1, root 3, and 2. And thus doing SOHCAHTOA on that thing, opposite over hypotenuse, you're going to get root 3 over 2. Okay, so maybe you did it with 120. Guess what else? You got root 3 over 2 for the answer. Guess what? If you do it for 420, you get root 3 over 2 for the answer. Did you do 480? Hopefully you did. You got root 3 over 2 for the answer. And finally, did you do negative 300 degrees? What is negative 300? We're starting here. We're rotating down clockwise now. And we, stop. Oh, wait a minute. We were just here. And we already did all of the steps. It's root 3 over 2. So what do you see? All of these different angles have the same ratio. So what if I said, what would theta be if we know the ratio is root 3 over 2? The answer is not 60. That's one of the answers. Because there's also 120, there's also 420, there's also 40, there's also negative 300. How many answers there are? There's infinite answers. It's a simple reason why. If you spin 360 degrees around the unit circle, you're in the same spot that you were. If you remember back in the last video, I said, why are we even doing this stuff? And I said, it's because these trig functions, when you have angles bigger than 90, can represent cyclical, periodic, real-world processes, things that repeat. And so here we see that when you spin around the circle 360, boop, you're in the same spot. So how can we represent that? We can't just say, I'm not here to write infinity answers down. I ain't got time for that. I got things to do. I got hobbies over here. So how can we do it concisely using fancy math notation? Okay. Well, I notice here that we have one triangle that was at 60, and we had another triangle. I can even draw it in our little unit circle up here. It had 120 degrees. And from the 60, if you tacked on 360, that's how we got the 420 degrees, that worked. Guess what? You could add 360 again, and then you'd get up to 780 degrees. That would work. You could keep adding or even subtracting 360, and you just keep getting answers that work. So how do we say that? We say you take 60 and go ahead, add 360K. Same thing to 120. You do extra spins. you're going to end up in the same spot. So plus 360k. Wait a minute. What the heck is this? This is just a fancy but efficient and concise way to say you can spin around the circle again and you'll be in the same spot. K represents some integer. If we want to get really fancy, how would we do this? We would say K exists in the set of integers, which I think you use this symbol for. Guys, I know some math stuff. I know a few little tricks. Now, you don't have to write this. This is just saying K is an integer like 5, 2, 0, -1, -3. It's saying any extra spins leave you in the same spot, and thus you have the same right triangle and the same ratio. So this is how we represent infinite answers. Now, we did it in degrees. We could also just do the same process and answer in radians. So what is the radian version of 60? It's pi over, it's pi over 3. Divide 180 by 3 and you get 60. And what about 120? That's 2 pi over 3. So how do we say an extra spin now? Well, a full spin is not 360. A full spin in radians is 2 pi. And we just say 2 pi k. K is just any number. If k equals 2, 2 times 2 pi is 4 pi. 4 pi plus pi over 3, that would equal, what would that equal? 2 pi over 3, 7 pi over 3? Yeah, 7 pi over 3. What does 7 pi over 3 means? That just rather than 60 degrees, you've spun around again and you've rotated 420 degrees. So you don't have to write this k business existing in the set of integers over here. I just did that for fun. But you have to tack on the 360k to truly show there are infinite answers. Just like in a quadratic, the classic x squared equals 9. If you answer x equals 3, dog, you're a noob. You're embarrassed. If I was your teacher and you do this in the next year, it's like I shed a tear every time. It's just don't. No, it's plus or minus 3. You got to have them both. You have to have the entire solution set. And now what's crazy over here is we have an infinite solution set. Not any angle will work, but there are an infinite amount that will. And we show that through the 360. Okay, so what are the steps of this process? They're the same as the steps from last time, backwards. I'll flash the steps at you, then I'll do a problem and we'll go back to them. I think that will be the easiest way to do it. Okay. So what are the steps? Well, for sine and cos, notice that the ratio they give you, it's got to be between -1 and 1 to start off the problems. Because on the unit circle, the x and y axis, it's only going to go from -1 to 1. Okay, what do we do? Step 1, make a mark on the x and y axis. Okay, maybe this will make sense when we see it in an example. Step 2, now draw 2 right triangles in 2 different quadrants. Okay, step 3, determine if calculator or not, if is it a calculator problem or not. We do this by just looking at the ratio they gave you. Is it one that you recognize from last week as a possible answer? Does it have noticeable things like 1, 2, √3 and √2 in it? Or is it something you've never seen before? That makes it calculator. Then we label central angles, doing SOHCAHTOA backwards. And once you have the central angle, you have your answer. You have the amount of degrees. You just might have to add 2 pi k or 360k for extra spins. So let's see that. What the heck does that process look like when you actually do that? All right, I'll show you. We'll do one. We'll say, what is theta? You could say x. I'll be fancy and say theta. It's a Greek letter. When it equals 1/2. Okay, step 1, unit circle. Cool. I've seen it before, no problem. Okay, I said the first step was make the mark. What are we talking about here? All right, this is sine. Is sine the y-axis or the x-axis? Correct. It's the y-axis. So can you look on this axis and can you estimate when the value is around 1/2? If this is 0 and this is 1, you mean just kind of like in the middle? Yeah, that's it, in the middle. Now, since we know that this is the height that our terminal points need to have, you can just go do, 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 and you can draw those points even with the mark you made. And once you have your dot, now it's like last week, we draw vertical segments, we draw unit circle radii, and that makes us have, yikes, 2 right triangles, 2 congruent triangles. Okay. Jumping back over here, we made our mark. We drew 2 triangles. Is it calculator or not? Let's take a look. Sine equals 1/2. Does that look like one of the ratios you got as an answer to the problems from last week? Absolutely it does. Okay, what do we do next? We need to find the central angle. We need to think SOHCAHTOA backwards. If sine, so opposite over hypotenuse is 1/2, that means the opposite from this angle is 1, and the hypotenuse is 2. Same from the right triangle over here in quadrant 2. The opposite of the central angle is 1. The hypotenuse is 2. Looking at it now, what type of triangle has these ratios, a 1-to-2 ratio between these? We know it's a 30, 60, 90, where our central angle is 30. Also, if you just kind of look at it, this looks like the 30-degree angle. And this one looks bigger. It's going to be the 60. Okay, so now we basically have our answer here. Theta equals 30 degrees for this triangle, and if we have a 30-degree central angle here, how far do we have to rotate to get there? You know, think if the whole thing is 180, take away 30, you got 150. Okay? Extra spins will give us a correct answer, so we tack on 360K. Now I want to show you another way you could have written this second answer. What if rather than 150 degrees, a positive angle, what if you wanted just to be a weirdo and rotate clockwise to this point? You can do that. What degree would you need to start here and rotate and end here? Well, it would be, I'll put a or. It would be negative because we're rotating down now, and it would be 180 plus an extra 30. That's 210. So if you wanted to, you could represent your little starting angle in a negative. Probably wouldn't do it for this problem, but maybe if I had an angle in quadrant 4, like I had one right here, rather than 330 degrees, maybe I would just call it negative 30. So that's a possibility. Both of these count as correct answers. Okay? Now, the problem didn't say if they want degrees or radians. I just did degrees because it might be easier for you guys to start with that to follow. But you need to know how to do radians as well. From here, we can kind of just translate it. 30 degrees is pi over 6. 150 is 5 pi over 6. Notice they got to have the same denominator, and we will tack on the 2 pi k for the extra spins. If rather than just rotating here to here, what if you want to spin around the circle and stop right here? Then you've gone pi over 6 plus 2 pi. Okay. Very good. All right, let's do a few others. I'll do them more quick now because you kind of see the process. We have a few variations, but they're all the same basic process. Let's say, what about cos of x equals, negative root 2 over 2. Okay? This one's a little tricky here because negative root 2 over 2, there's not one of the triangles that has 2 and a root 2 as the angles. You have to think backwards. This is the answer after you simplified it. If you unsimplify it, recall, it would look like this, 1 over root 2. And so that makes it a little bit easier to draw the triangle. So we'll start our process here. I'm drawing a big old unit circle. Okay. Now, when does cos have a value of 1 over root 2? Well, we know this is cos. We know it's an x value. So where does cos have negative values? Where are there negative x values? It's to the left. So maybe you don't really know how far 1 over root 2 is. You know, I could throw it into the calculator, and I could say 1 divided by root 2. It's actually 0.7. So I know it's, I don't know, it's kind of like here-ish. But it doesn't matter if you don't know exactly where to go, as long as you go, oh, negative, I have to go to the left. Here we can go out, we can draw our triangles. We can label from SOHCAHTOA backwards, since this is cos, this is adjacent over hypotenuse. The adjacent is -1. The hypotenuse is root 2. What type of right triangle is this? Well, we know this one's got to be 1 and 1 as well. You know, my circle is not perfectly drawn. This was an estimate over here at 0.7. That's why this right triangle here, which we know has got to be a 45, 45, 90. That's why it looks a little bit wonky. But it's good enough for me to figure out the central angle, because that central angle is our answer. Okay, so we started off, we made our mark. We drew our right triangles by looking at 1 and root 2. I knew this had to be a 45, 45, 90. Now all we need is our answer. Theta is going to be, this is 45, but you got to think, starting at our starting point, how do we rotate here? If we know a full semicircle is 180, take 45 off that and you get 135 degrees. For this one right here, we could go 45 degrees past 180 and get 225, but actually I want to rotate down, so I'll just say -135. Both are just as good. And then we tack on our 360. Okay, can we do radians? Yes, sir, we can. Our first one would be 3 pi over 4. Tack on the 2 pi k. And the next one, we could say -3 pi over 4. But maybe now I want to keep everything as positive, because I'm weird like that. So what would be the radians to go all the way right here in the 8-piece pizza? How many of the pieces? It would be 5 of those pieces. So 5 pi over 4. Understand that, look, -135 plus 360k, 5 pi over 4 plus 2 pi k is saying the exact same thing. Even though this one's degrees, this one's radians, this one's negative, this one's positive, it both brings you to that dot right there. What about tangent? Okay. Now on this little list, they have a little thing at the bottom for tangent. Tangent's a little different because its range, this is R for range, is all real numbers. If a problem asks you to do cos, like what is the cos that equals 2? We can't do this problem. This problem has no solutions, because on the unit circle, where is there an x value of 2? It's over here. It ain't even in the circle. We only go from 0, or really I guess from -1 to +1 for sine or cos. For sine or cos, they have to have ratios in between -1 and +1. Tangent doesn't work like that. Can you remember back to last week? If sine or cos are the y and x axis values respectively, what was tangent's geometric significance on the unit circle picture, the graph? Do you remember? We mentioned it briefly, and the answer was it was the slope. Because y over x equals tangent, and y over x, we know that's rise over run, that's slope. So, can you do a problem? Let's take a look, maybe like tangent of, I don't know, I'll say tangent of, look, I'll say x, just to be a weirdo. Negative root 3. Okay, notice negative root 3. That's bigger than 1. It's 1 point something. That would not be cool for sine or cos problem. It'd be instant, can't do it, no solutions, but it's okay for tangent. All we have to figure out here is where does the slope equal negative root 3? Which quadrants is the slope negative? It would got to be quadrants 2 and quadrants 4. So we just need to draw actually just one right triangle with the slope of negative 3. It's 1 point something. I'm going to just say it's like, I'm going to estimate it. I don't know, something like that. There's a line segment that looks like it has a negative slope of around 1 point something. We draw our right triangle. We fill in SOHCAHTOA. We know TOA is negative root 3 over 1. If it's just a number, you can put it over 1, and that means the opposite. Did I do this right? SOHCAHTOA. The opposite. Yeah. The opposite is root 3, and the adjacent is 1. I was a little weird for a second because I thought, wait a minute, negative root 3. But, you know, this fraction here, look, is equivalent to that fraction there. So that's actually what's going on. This makes sense in quadrant 2 where your y-coordinate is positive and your x-coordinate to the left is negative. Okay? So there's your negative slope in quadrant 2. That's a negative root 3. That's a 2. You can fill in the hypotenuse. You should know it. It's 2. What does this got to be? This is a 60. So our answer here is 60. Now you might say, why did you just do one triangle here? And the reason is for tangent, you only need to draw one triangle because the extra spins for tangent are just 180K and not 360K. I'll show you why. So look, here's the answer. 60 degrees plus 180K. Why can't I just stop there? Well, if you wanted to draw another radius slash hypotenuse that had a negative slope of root 3, we know what it would be in quadrant 4. It would look like that. Notice we just made a diameter through the unit circle. Okay? Going up to make a right triangle with the x-axis, we know you're going to have like the same triangle. This one truly has the negative with the root 3, and then the one over here is positive. It's another 3069. You say, okay, wait a minute, but this ain't 60. Also, look, I made a mistake. Did you see what I did? You're probably at home right now just freaking out. What did I do wrong? This central angle is 60, but our answer here, oh my gosh, how embarrassing, needs to be how much we rotate to get to that triangle. And clearly that's not 60. Rotating here is 120. Okay, so hopefully you were spazzing out at home when I made that mistake there. Good for you. We've kind of gotten sidetracked. We're trying to talk about this other triangle here. So take a look at this. What would be the degree for this triangle? You could say negative 60. You could say positive 300 if you want. But we actually don't have to write 300 right here as an extra triangle. Why is that? Because look. If you add 180 to 120, what do you get? Put your calculator down. Yeah. You get 300. So, not for sine or cos, but yes for tangent, one of the triangles is enough in your picture because that shows you the other triangle, because a perfect 180 rotation leads you to the other triangle. For sine or cos, it doesn't work like this. Like going back to the first problem we did, if you went right here to 135 degrees and you rotate 180 degrees, you're over here. There's no triangle over here. But for tangent, it works out beautifully where the other triangle is always a half spin away. So there you go. 120 plus 180k. And if they wanted radians, 2 pi over 3 plus now, not 180, but pi k. So there's a little variation we see with tangent. Notice its range can be bigger than 1 or less than -1. And you only really need to draw one triangle in your unit circle because of the 180k spin. We call this the period of the function, and you'll see that when we start graphing these things. Okay, maybe do just a few more and then we're done. And you can go live your life. / you can practice these on your own. Okay, I'll show you one. A little bit tricky here. Sine of √2 over 3. Now first, okay, √2 over 3, I don't really know what... I'm getting better at drawing these circles, I think. I don't really know what ratio that is. You know, well, it's positive. It's like a positive number. So where is the y value positive? It's in quadrants 1 or 2. If you wanted to, I could get the calculator out. √2 divided by 3 is 0.47. So we're kind of like a positive y value, 0.47, around 1/2. So we know we got dots here and here. That makes triangles here and here. Now here's what's unique about this problem. √2 and 3, that should look weird to you because we never see a ratio that has both a √2 and a 3 in it. We see 3 over √2, or rather, √3 over 2. We've seen that one before, √3 over 2. But the 30, 60, 90 has the √3. And the 45, 45, 90 has the √2. So we never see one that has both. So guess what? This isn't one of our ratios that we recognize. And when you see a ratio that you don't really recognize, what does it mean? It means you got a calculator problem. You got yourself a calculator problem. Okay, so let me throw on this TI-84. And yeah, you can see it well enough, I guess. And now we get to go to the TI-84. You get to do your favorite thing in the world, use the calculator. First, I'm going to hit the button right up there, mode. And in there, if you go here, you can select radians and degrees. I'll select degrees to start to make it easier for us. Okay, so we're in degrees. And now I need to figure out what's the angle that goes with √2 over 3. So I didn't hit sine. If you can take a look, I hit inverse sine, because this will give us the angle. Now we can plug in √2 over 3, hit enter, and it tells us a degree is 28.1 degrees. That means this central angle right here is 28.1 degrees. Now you say, gosh, why don't we just use the calculator on every problem? Well, sometimes these will be on no calculator exams, so you have to know how to do it without the calculator. Also, doing it without the calculator gives you an exact answer, and using the calculator, you got to round. So we know that's a 28.1 degree central angle, and we can say plus 360k. What about this other triangle over here? Well, they're congruent triangles, so if this central angle is 28.1, just copy paste, guys. That one's got to be 28.1. So the question is, how far do you rotate here to get a 28.1 degree central angle? And you know, if the whole top semicircle is 180, you can go to the 180 and just take off 28.1. Maybe we can do that right here. 180 minus 28.1. Okay, be a cool person. Do it in your head. That would be 151.9. Or you can just use the calculator. Obviously, it doesn't really matter. Okay. Yeah. So, that is our other triangle. 151.9 degrees, and we could add 360K to that. So do you have to draw the circle even when it's a calculator problem? Absolutely. Because looking at this picture is what helped me figure out, oh, I just do 180 minus this angle. It's the picture that gave me the clue to that. So on all of these problems where you solve, you have to draw the picture. Some of them you'll do without the calculator, some of them you'll need the calculator, but you got to draw the picture. Let's do this process with radians. Take the calculator out, hit the button that says mode, and go down, and I'll highlight radians. If you have a smaller calculator, you might have to hit a button that says like DRG or DEG or something like that, and then you'll say radians will pop up. We'll do the same, exact same problem. Let's just check it out. It's just inverse sine of root 2 over 3. Hit enter, and now we got 0.491. Now that is radians. Let's write it down first. 0.491. I know it looks really weird, but that's an amount of radians. When the calculator gives you an answer in radians, it doesn't say pi over some number. It just straight up gives it to you. You know, 2 pi is 2 times 3.14. So 2 pi, you know, is like 7.28. You could write it as 7.28, but we're cool when we write it as 2 pi. So, you know, if the full thing is 7.28, if a half circle is 3.14, then a quarter circle is like 1.6-ish. So just understand, this is an amount of radians, and just kind of use pi as 3.14 to help you estimate it. So there is our quadrant 1 triangle. How do we figure out this over here in quadrant 2? Well, we do the same thing we just did. For degrees, we said 180 minus this little angle right here. You do the same thing for radians. Not 180, but we're starting off with pi and not 28.1 degrees. Now we're using 0.491 radians. Here, absolutely, going to the calculator, pi minus 0.491, and I got 2.65 radians. Kind of makes sense to me because I know a full 180 is pi, aka 3.14. So if this is 3.14, then 2.7, it's getting close to it, kind of looks right. So once again, this was a no calculator problem. You still draw the picture because it helps you figure out both of the triangles that you need. Do another one quickly. What about tan equals 2.7? Now, this obviously is going to be a no calculator problem because 2.7, that is not a ratio we see. So sometimes it'll be, this first one is kind of like a little trick because root 2 and 3 are familiar, but you just never see them in a fraction like this. 2.7, I don't know where that is. I could draw a picture real quick where the slope is real steep around 2.7. Okay? And then we can just go to the calculator. Now, I'm going to add a little detail to this one. We call this detail a domain restriction. Sometimes they won't want infinite answers, and instead they'll restrict your answer to between 0 and 360 degrees, or between 0 and 2 pi. They'll give you a little window on the domain where they just want the answers that exist in between the values they give you. And I know this video is long, guys, but I'm trying to hit you every detail possible. So we'll say on this one, I'll say I'll just make it simple, between 0 and 360 degrees. That's how they'd say it, like that, using an inequality. Okay, so what do? Well, you just kind of do the problem like normal. Okay, we drew the slope of 2.7. You can go to your calculator now. I need to put the mode back to degrees. I need to do inverse tangent, and I hit 2.7, hit enter, it tells me theta is 69.7 degrees. And if we had infinite answers, we could say, okay, plus 180K. But guess what? We're not done. We don't want infinity answers. We only want answers that are between 0 and 360. So we go one step a little bit further, and we say, using our infinite answer expression, how many angles fit between 0 and 360? Well, clearly, the first one of just 69.7, that works if k was 0. Okay, what else? If you add 180 to our expression, you get 249.7. Guess what? That's between 0 and 360. If you add 180 again, you get 429.7. Technically, it is an answer, but it doesn't fit in this window, so we don't put it. So here, we actually only have 2 answers that fit in the window they gave us. Okay? You got any more? I can do you one more. What a boot if you see something like cosecant. Cosecant x equals 2. Now, normally you'd say, hey, cos can't be equal to 2. That's outside the range. You're right. But this ain't cos. This is cosecant. Cosecant is really 1 over sine. So since cosecant is 1 over sine, we can do this the long way rather than cosecant here. I can write 1 over sine equals 2. And if you want to get sine by itself, you can multiply sine by both sides. Divide both sides by 2. And here's the real problem. Sine equals 1/2. Hey, that's something we can do. A faster way to do it is just, you make this go from cosecant to sine, and then you just put 1 over whatever you got. So you don't have to do the full algebraic process every time. From now, we've turned the problem into one we already know how to do. When does sine equal 1/2? Y equals positives up here. Boom, 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 boom. SOHCAHTOA, we know that opposite over hypotenuse, we know the opposite is 1 and the hypotenuse is 2. That means we got to have 30, 60, 90s right here. That's 30 and that's 30. Let's imagine the problem had a domain restriction. Okay, I'm going to throw it on there. I'm going to say we want answers between, we'll say, negative pi and pi. That's our restriction. The problem would, I made this up, but the problem would provide you with this. If not, you're putting infinite answers. Okay, so if we put infinite answers, we would have this, 30 plus 360k and 150 plus 360k. But we need to figure out which of these fit between negative pi and pi. Notice, negative pi over pi is at degrees or radians. Clearly that's radians, so our answer needs to be in radians too. So rather than 30, we're going to say pi over 6. Okay, so let's do that. This is like between negative 180 and positive 180. Which ones work? Okay, well, 30, that's pi over 6. What about over here, 150? We could call it 150, or we could call it negative 210. Which of those fits in this domain window between negative 180 and positive 180? Positive 150 or negative 210? Well, clearly positive 150. And we're talking radians, so we're talking 5 pi over 6. If you're still hazy on going quickly between radians and degrees, notice I'm just using them interchangeably. Just go back and study up on that a little bit. But to write out the inequality, why are we taking 150 as our answer? Because look, 150 works in this inequality. Yeah, it's between negative 180 and positive 180. But negative 210, even though it's an answer technically for infinite answers, it doesn't fit in the window right here. So we reject that, and we only get 2 answers right here. That's all I got, guys. I really hope everyone's doing well, is safe out there. To recap, solving means you're trying to find the angle. Infinite answers are definitely a possibility. We got a lot of variations. You got to start the process by making that mark on the X or Y axis. That's probably the most important part. And then you're just doing the process from last week in reverse. Hope these help. Practice some problems and enjoy yourself. Peace.